This is ETM 11 about making predictions with bar charts and equations. Notice this is a little spicy. This is like AP level-ish, like challenge level-ish work. So it's not so bad, but if it seems difficult, that's why. Doesn't mean that you shouldn't take it on. It means that you should spend some more time with it. Notice this says that we want to connect our thinking to ETM 4 through 7. So just to remind ourselves, ETM 4 is about kinetic energy, and we saw this example down here about how to use this general equation. Baseball has just left a pitcher's hand, moving at a speed of 40 meters per second. We know the mass of the baseball and gravitational energy is here. The idea is that we can use all of these general equations that we went over in ETM 4 through 7 or 8 or whatever it was with our bar charts to think about how to make predictions. So let's do an example here. The pitcher in ETM 4 throws the ball straight upwards. Instead of throwing it towards home plate, this pitcher throws the ball straight upwards. The question is, how high does the ball reach? And I do have some information here that's going to help me solve this problem, but I want to start by drawing a picture in a bar chart. So I've got this picture here. Let's say she's throwing the ball upwards. It's moving at a certain speed in the beginning, and at the top it reaches a certain height. So we want to call this moment A, and we want to call this moment B. Next, I'm going to draw a bar chart. Oh, well, let's make sure to do this. Let's say my EG equals 0 line is at the initial height of the ball. And then I want to draw a bar chart. So I'm going to say EG, let's actually start with kinetic energy. That's my bad. EKA plus EGA equals EKB plus EGB. I know that we've got some kinetic energy at the beginning and zero kinetic energy at the end because the ball's not moving at the top. I know I've got zero gravitational energy at the beginning and the same amount of kinetic energy that I started with at the end because all of it is in gravitational, assuming that zero energy transferred to thermal. This is all review so far, but what we're able to do here is essentially what we saw in ETM 10. We can leave out any zero value energy forms and set the two moments equal to each other. I've already set them equal to each other. What we're saying is EKA equals EGB. Now, since we know some general equations for EK and EG, we can do one better. We can actually refer to ETM 4 and say, I know that EK is equal to 1/2 times mass times speed squared. So I'm going to actually write down below here 1/2 times mass times speed squared. If you prefer to write this out with letters, you can. But I'm taking this value, and instead of just writing EK, I'm writing the general equation that I know is equal to EK. So you can imagine a little equal sign here, saying that EK is equal to 1/2 mass times speed squared. I also know that EG is equal to mass times G field times height, so I can substitute for that as well. I can imagine that little equal sign and say mass, which we abbreviate with an M, times G field, which we abbreviate with a G, and times height is the same as writing EGB. Now, just to clarify to myself, I'm actually going to say, okay, the speed at A and the height at B. If I was dealing with a bunch of heights and speeds, this would help me because I could like differentiate between the height at B and the height at A, for example. But I don't really have to worry about it because the height at A is 0, so I can kind of ignore that fact. But this thing that I've created here is kind of magical. This is going to let me make predictions about, for example, how high the ball reaches. So let's actually, we'll deal with this equation in a second. We want to move things around so that we get height all by itself. So it becomes an algebraic problem of trying to get height by itself on one side. Let's do some of that work over here. If I write 1/2 mva squared equals mghb and divide both sides by the things that are attached to height on this side of the equation. So I'm going to divide both sides by m and g. I can see two things interesting happen. First of all, these both divide out to 1 on this side, so they cancel. And then on this side, actually, the mass cancels too. Interestingly, if I'm trying to solve for the height that this reaches, I can tell 1/2 VA squared divided by G is equal to the height at B. This is a general equation that I've figured out for determining how high a ball reaches. And I started with a bar chart. I substituted algebraic models to get this thing that allows me to make some predictions. Now, to do a little bit better than this, I need some actual quantities to substitute and solve. So let's look back here, and I can tell, okay, the speed is 40 meters per second, so I'll say V equals 40 meters per second. I should say that's VA. And I know the mass, but interesting, I don't actually care about the mass. The mass disappeared from this. It doesn't seem like the height the ball reaches depends on mass, which is kind of fascinating. But I can tell over here that since we're playing baseball on Earth, the G field is 10 newtons per kilogram. So I can say G equals 10 newtons per kilogram. Got some funny units going on here, but this does allow me to general equation, substitute, and solve. Notice I had to do a little bit of funny manipulation to get my general equation before I did any substitution, but once I got it, it's pretty straightforward. 1/2 times 40 meters per second, and I'm going to make sure that I square this, divided by 10 newtons per kilogram. These units are going to be pretty weird, but I know at the very least that the numbers work out the following way. 0.5 times 40 times 40 divided by 10 equals 80. So 80 equals the height at B. Now, I want to point something out here, because what I've got on this side, if I'm trying to actually think about my units, is a huge mess. If I'm actually trying to think about the units here, I get meters squared per second squared divided by newtons divided by kilograms. It's a whole crazy mess. And if we were to go through and figure it out, the units would actually work out in a way that makes sense. It is super complicated here, so I'm not actually going to freak out about it. What I am going to do is say what unit does make sense for height. I know that the unit that makes sense for height is meters, so I'm just going to write down 80 meters. We're saying this pitcher is able to throw the ball upwards 80 meters, which is crazy, crazy high. That might not even be true. It might not actually be a valid assumption that zero energy transferred to thermal, for example. It's more likely that there was some interaction with air resistance, and this isn't actually 100% of the value of this. I could draw a different bar chart for that. I could figure out how much of the energy transferred to thermal. And that, by the way, is what we're going to be dealing with here. This word efficiency is a way to refer to, in general, how much of the energy that started as kinetic transfers to gravitational. So we'd be able to take this example and make a different assumption. Maybe 80% of this makes it to this. And for the prediction Olympics, that actually is a really, really important part of doing the most sophisticated work. But here you're seeing bar chart to general equation is a hugely powerful step. Starting with a bar chart and then making a general equation out of it, moving some things around and then substituting is a big idea. It's difficult, it's a little spicy, but you can handle it. My suggestion would be, in order to practice this, in order to see how this might work, I would recommend using this space, this big space below here, to do another example. If I draw a line here, we can tell this is still about solving problems with conservation of energy, and we used it to just show how we can think about specific energy values to solve for example, how much energy transferred to thermal. You can see that the idea is the same. We're still going from bar charts to algebra, bar charts to algebra. This algebra is a lot more complicated, but I would give yourself another example here so that you can practice doing this process and check it to see if it makes sense to you, and have another example in your notes for any assessments that you might come across.